Okay, I'm going to see if this is going to work now. YouTube sometimes just thinks that it detects copyrighted information and it just shuts the stream down. I don't know what that would be on here, but it's because the technology is running the thing and not people, so they don't know better. I don't know if anybody's going to find this now. It's been a lot of hassle. I'm going to try again in the morning, but let me get a couple of ideas out there at least, and then I got to try to get set up for another class. But this concept of inverses is what I was talking about here. You want to remember this from earlier in the chapter. Turns the graph around. Points on the graph get switched around that way. But also switching x and y can help us if we need to find the inverse function. By taking something like f of x equals 2 plus 3x, writing it with input and output variables, switching the variables now. So that y is my regular function of x, but I'll switch it over to x equals 2 plus 3y, and this y will be my inverse function. So then I got to solve for y. This y is my inverse function, so now I know that f inverse of x would be x minus 2 over 3. That's the inverse of this function. That can be checked. So that process of finding inverse functions, usually a little bit more complicated than that because that was a pretty simple thing to start with. But that process can be used to find the inverse function for a given function. So that was earlier in the chapter, and we haven't gotten a chance to kind of go back over that a little bit. I wanted to remind you of that because that'll be on the test here along with exponentials and logarithms. We do that same thing with exponentials and logarithms. If I start with a function, let me just follow that same process through with something that starts off as an exponential, like f of x equals 5 times 3 to the x. If you write that as y equals 5 times 3 to the x, your original function, then you can go over and look at the inverse function of that. X equals 5 times 3 to the y. Getting y by itself like this is going to require switching over to log form. So we can divide by 5, x divided by 5 equals 3 to the y. And then writing that in log form, base is 3, the input becomes x over 5, and the output becomes the y over there. So that is my inverse function for that one. That would be a log base 3 of x over 5. And this switch over between exponential form and logarithmic form was a big deal. That's how we solve for a lot of things, is being able to go back and forth between those two forms. So that was a major topic in the early part of the chapter also. Allows us to solve some of these equations, just being able to do that. For example, I wanted to get into the equation solving part of this. So 5.6 number 7. Oh, not numbers. Yeah, 5.6 number 7 is what I was looking at in the book here. An example of the simpler equations on this stuff. Log base 2 of 5x equals 4. We're just trying to solve for x in this thing. So I want to find the x value that'll make that come out to 4. But it's got a log term and it's got this number over here. So the only way to get rid of the logarithm is switch to exponential form here. That's the simplest way to get rid of this here. We're going to rewrite that expression into exponential form. So this is equivalent to base is 2. Input to the exponential would be the output of this one. And the output of the exponential would be the input of this one. So that simplifies to 5x equals 16, we can solve for x. Now that switch over there usually does the trick to get the x out where you can solve for it using normal algebra stuff, doing stuff to both sides and working regular equation stuff from there. So x equals 16/5. If you substitute that into the original, that's going to be the solution to that equation. Now, the other thing we want to remember with these things is the graph stuff about both of these kinds of functions. So let me think about, as long as we've got this example in front of us, we can think about how this function would work. If I graph the function log base 2 of 5x, what would that thing look like? So that's our function log base 2 of 5x. Your key points for a logarithm function would be when the input is 1, the output is always 0. And when the input is the base, the output is always 1. So look, I'm going to need the input to be 1. I'm going to need 5x to equal 1. That would be at 1/5. That's when I would get 0 from it. And when the input is the base, 2, that's when I would get 1. So when 5x equals 2, that's at 2/5. That's when I'm going to get 1 from it. And the input's always greater than 0. That's the other key feature on logarithm functions, is they have that asymptote at x equals 0, and they're only defined when the input is positive. So this one's got an asymptote right here that it doesn't go past. The function is on this side. It's 0 at 1/5. And it hits 1 when you get out to 2/5. And kind of continues in that direction and has the asymptote here. So that's what the graph of that would look like. Where it's equal to 4, it's not going to take terribly long to get to 4. That would be the answer that we got up here. The 16/5 would be where it's equal to 4. That's not too far out, that same graph. So we could think of it graphically and remember the properties on that thing. If you took your basic function, I'm just trying to tie this together with a bunch of ideas because I have a short amount of time. I want it to be useful for something. And if you got some questions, you can drop them into the comments here, and I may have time for it now. I may have time for it to get back to it later. This sort of thing, the 5x in here is a horizontal compression of the function. So your base function log base 2 of x would go through 1, 0, and 2, 1. Those would be the main points for a regular log base 2 of x. Whatever the base is gives you 1. These would be the points on the main function there. That changing that to 5x in there is a horizontal compression. So you see our x values got compressed by dividing them by 5, and then the output stayed the same. So you can see that regular log graph, which would go through 1, 0, 2, 1, got compressed horizontally. It got flattened down to here to get that transformed logarithm function. So that ties back into the transformations that we did before. That's good to remember. All right, so I still need a test time from a few people. If you're out there catching this and you haven't let me know which time or you want to take the test, I got several of you down and I replied to those. So let me know when you want the test. I'm going to email that form out. I email the test out to you at the beginning of that time slot, and just pictures of it and send it back, or scans, whichever you have. One other equation concept while we're at it. We use the idea that if you can get something written as log base whatever of one thing, if you can get your equation in this form, then you can cancel the logs and just solve for x from there. But you have to do this with just a single logarithm on both sides. So that's when we had to use our properties to rewrite stuff. The property says you can cancel these because they're one-to-one functions. Applying that, you have to be a little bit careful with application of that thing. And that's what we use when everything in the equation has a logarithm on it. So something like number 32. I'm still in 5.6, but number 32. Solve each logarithmic equation. This one says log base a of x plus log base a of x minus 2 equals log base a of x minus 4. Now, I want to use this property right here, but I can't do it with separate terms. This sort of doesn't distribute right there. I have to have just a single logarithm here. So somehow I have to funnel these things together into a single term. This side is okay. That's a single logarithm. This side needs to be just log base a of one thing. And the property that says what to do right here was the property that says when you're multiplying, you add the logarithm. So this addition turns into multiplication. So that's x times x minus 2. Once I have them put together like that, then I can cancel x. The only way this could be true is if x times x minus 2 was equal to x minus 4. Now I got regular equation. I got regular algebra stuff I can do from there. If I get everything to one side on this, I got x squared minus 3x plus 4 equals 0. That factors nicely. So it has these two roots. X equals 4. No. Yeah, that's fine. No, it's not. Those are the wrong factors because I got a positive 4 up here. I'm sorry. Got a little carried away there. Does that factor nicely? Doesn't factor nicely. Copied the problem down wrong. That's the problem. Copied number 32 down wrong. So this would be a quadratic equation situation because that doesn't factor nicely. That's not what we're supposed to be doing. Because the problem actually had a plus 4 in here. So let me go back and make that edit. I'm actually supposed to be doing this problem, which had an x plus 4 in there. That should be a negative 4. That's what it should have been. So that does factor. One more point to be made on this. The roots now are x equals 4 or x equals negative 1. But only one of those is going to work in that original equation. You can still see it up here. I think when x is 4, that's going to work just fine. Everything's positive. But when x is negative 1, a couple of these things would be log of a negative, which isn't even real numbers. So that's not in the domain that we're looking at there. That one's not in the domain. This one is the actual solution that we would have right there. All right, so I got to get set up for another class to come up here. So that didn't work out like I'd planned today at all. We had 800 customers without power down around this area. And I don't know why yet, but we're back on. And this is here to watch. And tomorrow morning around 10, I'll try to be back on again. Let me know if you caught some of this. If you got further questions, if you got topics you want to go over from that practice stuff. And a couple of you need to let me know which time slot works for you on the test. So check that out in the announcements there. I will be back in touch soon.